Okay, welcome again, everyone. Thanks for your attention. Nice to see many familiar and new people in the list of participants of this retronetcall tonight. I'll go through a couple of slides, just very high-level introductory, what this is about and why we're doing this, for the benefit of future viewers who are not participating live and who are not yet part of this community. And then we'll go into the actual topic of the presentation. So a quick slide about who I am, which will just be on the record. I'm not going to read that now. So some background. So what do we call retro networking? Well, basically, there are many people who enjoy retro computing, and the focus is on the historical computers, whether real or emulated or combinations thereof. But then what is the computer without communications technology? At least to me, that has always been the exciting part. Computers get so much more interesting when they're connected. So retro networking is just the same like retro computing, but focus on networking and telecommunications. And that's, of course, a very wide area. What we're looking at tonight is primarily ISDN TDM network retro networking, but of course there are other ways of retro networking. Why would one do that? Well, as usual, because you can, and also because it's I think a very relevant topic. That the communications technology has been very important to computing ever since at least the 1980s. When home computers and PCs were used with acoustic couplers, modems, ISDN adapters, and so later ISDN adapters and so on. So we have all of the client-side equipment still rather readily available. You can go on eBay and get network interface cards, modems, ISDN terminal adapters, video telephones, fax machines, and so on. So that's still something that's available, usually at a very low expense. To me, it's personally, it's because, well, I was using all that stuff back in the day, but now I'm a senior developer with a lot of experience in implementing telecommunications protocols, and it's fun to go back actually running that or even developing parts of all that old technology that back in the day I was just using. So yeah, the more serious reasons is, from my point of view, that there's more and more technology in our society today, and I think preserving the knowledge about the historical technology is important to preserve like any other cultural history. The window of opportunity for a lot of the stuff is closing, so equipment is harder and harder to find. The software for old technology is often more difficult to find if it's not consumer equipment. If it's more, let's say, operator side equipment, telco equipment, it's already difficult or impossible in some occasions. But yeah, the time is running, clock is ticking. So something that we should do now rather than later or complain about the fact that we missed the opportunity. Okay, so that for the brief high-level introduction. So this is a diagram from the OCTOI homepage. OCTOI is the Osmocom Community TDM over IP network. That's basically what we're talking about. This is a very high-level abstract diagram. So we have some people that I'm called hobbyists here, A, B, and C. Some of those are here in the list of the participants tonight. They have some PBX, or most of them have a PBX at home, a private branch exchange that is large enough to have an E1 trunk interface that used to go to the public telephony network back in the day when such interfaces were available. And instead of connecting, so in the past, we would basically have had that upper part of the diagram and the public ISDN network at the bottom. But since the public ISDN network doesn't exist anymore in many places, we have to basically emulate the lower half of this diagram, meaning from this E1, we don't attach to a public network, but we have some access device in quotes that consists of several parts. And that allows us to interconnect these PBXs and all the modems, ISDN terminal adapter, fax machines, and whatever is connected behind them over the internet to something that is currently a virtual machine called DIVF. That's a German postal acronym for a long-distance central office or long-distance switch in the old days. So a digitale Fernvermittlungsstelle for those who want to know the German word. And so we call the host that's running all this the same way. And on this, we run a bunch of software, and that's basically what I'm going to cover tonight mostly. If you want to join this network, you basically have to get a private branch exchange that has an E1 interface, or sometimes called primary rate interface, or S2M also in Germany, as also synonymous in this context. Then you need to get an E1 USB device or build one yourself. It's open source hardware, and some embedded Linux device. That could be a Raspberry Pi of any generation, or a BeagleBone, or a NanoPi, or whatever, some embedded Linux device. Or you can also, it doesn't need to be embedded, something that runs Linux and has internet connectivity and has a USB host controller. That's sort of the minimum requirement. And then you connect this together, and you can basically participate in the network and make and receive calls through this device. So let's first look at the bottom layer, the physical layer, so to speak. In a traditional network, it would be the TDM layer, so the time division multiplex layer. That's basically just the transmitting bit streams between different endpoints. Right now, this machine that we have, the DIVF, it terminates 16 physical E1 lines. Those are two 8-port Digium PCI Express E1 controllers. Not all of those 16 ports are used. Just put them there so we have the capacity. I think we only use 3 or so at the moment. And then we have currently 24 virtual E1 lines, which are basically these hobbyists that we are talking about here. So each of those hobbyists has one virtual, they have a physical E1 line, but it's usually just a couple of centimeters between the PBX and this ICE1 USB here called access device. And that gets forwarded over the internet to this central machine. And in this central machine, currently we have 24 such virtual E1 lines going to 24, almost 24 different. Some people have 2, so maybe about 21 or so different users around the world. Yeah, so the setup at the subscriber side, if you look at it in a bit more detail, so we have some PBX or some other E1 speaking equipment. That could be a Cisco router or a media gateway or whatever that speaks E1. Then you have a physical connection to this ICE1 USB device that converts it to USB transfers. And then there's a software called Osmo E1D, which receives those E1 frames received over USB, and then does some processing and sends it over IP, over the internet, to a remote location. In addition, there is some compression or some, well, it's not, yeah, we could call it compression, but at least it's removing redundancy so that unused time slots don't get transmitted over this, over the internet. Usually even a, how can I say, a rather enthusiastic hobbyist will unlikely use 30 B channels or 30 concurrent calls from their PBX at home. So it would be a waste to transmit all those unused circuits. So we do some detection and reduce the traffic here, so that in the idle case we don't, or half idle case or whatever, we don't use all that bandwidth in both directions all the time. Yeah, so this is set up at the subscriber side. Now, in theory, of course, we could just do the same setup at the central office side. In the end, it's the same. But then it means we end up with physical E1 circuits. And initially, when we started this project, it was actually the setup that we had, basically this setup at the subscriber, and the exact opposite again at the central hub, or central machine, central switch. That was in my basement, but at some point it becomes rather expensive with all those physical E1 circuits and embedded Linux boxes and cables that all have to go into then physical E1 line like a DADI card to go into the switch, so it doesn't really scale. And that's why we developed something called dahdi-trunkdev. That's a custom extension of DADI. Normally DADI or DHDI is the Digium asterisk hardware device interface or something, like hardware driver interface. I'm not sure what the acronym stands for exactly, but usually it is a layer between a physical line interface card that could be PSTN, that could be ISDN, basic rate, primary rate, any kind of telephony circuits. So between some physical hardware that attaches to a line and software such as Asterisk or FreeSwitch or Yate or some Osmocom software or whatever you want. So it's just an abstraction of hardware interfaces. And with dahdi-trunkdev, we modified it in a way that we don't have the software, in this case Yate, the soft switch, using DADI, and then DADI talking to some hardware, but actually we have another software interface. So we have a software interface to Yate, and we don't have a hardware interface at the other side, but we have another software interface that's called trunkdev. And this other software interface we can then match, can use by Osmo E1D in the same daemon that we use with the ICE1 USB at the other end, which speaks the same protocol, this OCTOI protocol. So basically we receive these compressed or redundancy reduced E1 frames over the internet. They go into Osmo E1D, and Osmo E1D reconstructs the full E1 frames, meaning 8,000 times per second, 32 bytes E1 frame. And those E1 frames are then sent over this trunkdev character device into the DADI, which is part of the Linux kernel, which then offers the normal DADI user interface to a soft switch like Yate in this case. So for Yate, or you could do the same with Asterisk or FreeSwitch or whatever you want, but for the soft switch software, this software doesn't know that it's not talking to a real physical E1 channel that's locally in this machine attached by hardware. It looks exactly the same. So there's no modification for this in Yate. And it's just some custom code here, Osmo E1D, and this modification to DADI. So it doesn't talk to a local line. So in the end, we create a setup. If we go back to the earlier diagram, we create a setup where we have a subscriber hobbyist here with a PBX that has a physical E1 circuit, and that gets magically transported over here, and it becomes a virtual DADI trunk locally here at the central soft switch, so that it like this, the physical E1 circuit that appears here at the subscriber just looks like it's a local E1 circuit here at the soft switch at the DIVF. And yeah, so as said, to Yate or to the soft switch that you use, it looks exactly the same like any other physical E1 circuit. Now, ISDN is, of course, not the only protocol that we can speak over this. So up to this point, there is nothing ISDN specific in this setup, meaning that we can use also other protocols over E1, and we have also tested that. So, for example, we have set up some frame relay, a frame relay being another retro networking technology. So you can basically have your Cisco router with a physical E1 circuit, feed that into Osmo E1D, and then we have here a network device. So instead of having the B-channel time slots here, DADI already has a support for this for decades, that you can then expose individual time slots or bunches of time slots or the entire E1 line as a network device. And then we can run IP over that, or we can run other protocols over frame relay that is fully supported and is working as well. As said, today we talk about the ISDN application on top of it, but as said, we can do other stuff. So if you have some exciting legacy equipment that does something non-ISDN over E1, then we're more than happy to look into that. So now we're going into ISDN, basically. That is what we run on top of it today. So 90% of the E1 lines that we have, these virtual E1 lines, or even the physical ones, actually all of them are used for ISDN, meaning that there is a signaling channel, the so-called D channel, on time slot 16 with Q921 lab-D protocol and Q931 in the European DSS1 flavor on top of it. So this is the signaling protocol stack that was used on ISDN interfaces in the public ISDN networks. This is exactly what we speak here. So from the interface, from the soft switch to the DADI side, we have one time slot with time slot 16, which is operated in HDLC FCS mode. That means that the kernel implements it's a standard feature of DADI, nothing specific to this setup. So the kernel implements a software HDLC decode in the kernel, and then the kernel device only reports data to the yate in our case, or to this, whatever software you run on top, if a full HDLC frame is received, and there's no overhead or no system calls all the time if there's no actual signaling data on the signaling time slots. All the other time slots, meaning 1 to 15 and 17 to 31, are configured as P channels. So those can carry calls, whether voice calls, ISDN video calls, data calls, analog modem calls, fax calls, whatever you want on those B channels. So yate, as I mentioned already many times, is used here in this. I used it after playing a bit with other soft switches and their ISDN support. And its implementation is far from perfect, but good enough for most of the use cases so far. Definitely we need to improve some, but it's definitely much more complete than FreeSwitch or libPRI, which I believe is also used by Asterisk. So there are even more gaps at that end. Actually, a very early setup that I did in this context, I was using FreeSwitch, and I had to do a lot of patching to get it to work at all. And then there were still so many bugs and so many shortcomings. I was not very happy with that in the ISDN case. So yeah. The setup then is connected not just to the user PBXs that we have, but also to a couple of physical machines that are next to this DIVF system. Actually, let's have a quick look at how this is physically, how this setup looks physically. So let me just open the browser here. Is the co-located hub? That should have some, yeah, there we have some pictures. So you can see that, well, this is, yeah, again, the problem with this image viewer, but so we have at the very bottom, there's the Portmaster 3 machine, then we have some server PC, some more PC hardware, and up here there's the Cisco AS5400. And now let me figure out which one was the this the bottom. So this 2U server here on top of the Portmaster is a server called AVST, which is again another German postal acronym, Auslandsvermittlungsstelle, so the International Interconnect Switch. So that is the physical machine on which we run this DIVF soft VM. Yeah, there's some more pictures here, but I'll spare you of that now. No, this is again, yeah, sorry, it's in the browser, not outside of the browser. So, yeah, now we have also since recently, and that is news, we have 2 ISAP SS7 interconnects. So instead of, it's also using E1, of course, but instead of the ISDN Q931 signaling, we have the SS7 protocol stack there, meaning MTP2 as layer 2, MTP3 as layer 3, and the ISAP protocol, the ISDN user part, as signaling protocol on top of that. In this case, we use both TS16 and TS1, so 2 time slots as signaling channels. So we have redundant links within a link set. So in SS7 MTP, everything is, all the connections are so-called link sets, and yeah, always like have, I think, up to 7 or 8, I think, possible links within a link set, and the idea is that you have redundancy between those links. And the problem is if you have only one link and you have errors on that link, which in our case happens quite often due to lost packets, for example, on the internet, then the link goes out of service. And if you only have one link, then basically you cannot communicate anymore until it has recovered. And by using two links, when one link is declared as dead because it has too many errors, it can basically fail over to the second link and the communication continues. This was suggested by Jan, and it has significantly improved from my point of view compared to what we had before. This setup is now used to connect two EWSDs. One is configured as an international interconnect to the Czech Republic of Jan, who is here also today. And the other one is a national interconnect to the EWSD of Jolly, which is located in the north of Germany in Dörphof. Yeah. Aside from that, we also have another protocol to interconnect with the CNET or CKTS, which is an international telephone connectors network. Most of the people there are interested in analog phones and use asterisk to interconnect via this CNET. And technically, this is implemented by using enum to resolve the called party. So enum is a technology that allows you to resolve a telephone number to an IP address using DNS. And so this is used to route calls. Everyone who operates a switch in this CNET network, like us, registers there, and then you get entered your IP address, the server IP address, in a DNS zone file. And this means anyone calling a 4930, so the Berlin prefix or the Dörphof. Yeah, sorry, I forgot to replace the fix me. I didn't recall off my head the prefix of Kiel, which I also added here, and Nuremberg. So those prefixes get routed to this DIVF machine or DIVF machine. Yeah, 431. Sorry for that. And then basically the DNS resolution points to the IP address of this machine. And then the actual call is established using the IAX2 protocol, which is an asterisk, originally asterisk specific protocol, but it's also implemented by Yate and others to get the call transported over to us. And the same way also works the other way around. So if we have an outbound call to any number that we don't serve locally in our switch, or where we don't have a route, a direct route, it goes to the enum route, and it will do this DNS lookup, try to find if there's an IP address responsible for this call party number, and if yes, then it will deliver the call using IAX to that IP address that's stored in the DNS. So what kind of problem areas do we have at the moment? Well, we have some Q931 incompleteness in yate. Those are usually easy to fix once you discover them. We have now, since we have ISAP, there are some Q931 to ISAP interworking problems. I guess yate was mostly used either between SIP and ISAP or between SIP and Q931, but not really between Q931 and ISAP. Because that's what you had the real world large scale central office switches in the public ISDN network. So this is a configuration that works, but is not very well tested, I guess. And this means we run into some bugs there. Those are a bit harder to fix due to the architecture, where you need to basically pass data through, I don't know how many layers of abstraction between the Q931 and the ISAP code. Overlap dialing, we only support on Q931 at the moment, not on ISAP. That should be possible to fix, but nobody has found the time yet. And we also have some other bugs that I don't want to go in detail. What I personally find particularly annoying is that yate uses so much CPU for doing nothing. So it uses about, well, actually it's more like 12% of one CPU core for each E1 line that we have, even if it's completely unused. And I think it's just very lazy programming style. So hopefully that will be fixed soon. Because it will limit our growth, of course. If more people attach to the network, we will eventually run out of CPU cores in this machine. Yeah, so then we have, next to this DIVF, we have two dial-up servers. One is a Livingston Portmaster 3 and the other one is a Cisco AS5400. Both are attached to the physical E1 lines, and we use only the Portmaster at this point. The Cisco is powered off because it consumes so much power. We can switch it on at any time somebody wants to use it, but as long as nobody has a use case for it needing it, I think we can spare 400 watts of power consumption. I mean, we get sponsoring from an ISP, but we shouldn't. Still, we should have a look at the environment and not abusing it if we don't really do anything with it. So the Portmaster has this interesting feature that it has a radius-based lookup based on call number. What this means is that we can implement hundreds or even thousands of services in this single Portmaster device. Every time a call comes in, the Portmaster will ask the radio server what it should do with this call, and the radio server can then tell it, well, forward it using this protocol to that IP address, or terminate it as a local PPP call and hand out this IP address to the user, or things like that. So it's a very, let's say, programmable or configurable in that way. In theory, the Cisco should also support it, but I think I wasted more than a few days of my life already trying to make it work, and I'm very confident that at least in those software versions that I tried, it is actually not working, despite the documentation claiming it does. So that actually is a bit of a disappointment. Consumes a lot of power and doesn't do what it's documented to do. So yeah. Yeah, just some contact slides in case somebody wants to get in touch. We have a discourse forum that you can can discuss with us. We have an IRC channel. There's the retronetcall in which this presentation is made, and you can also reach out to me personally. There's some further reading links, which I'll just leave on the slide for a second in case somebody watches the video later. Not sure whether, yeah, and the end of file, that's it. So yeah, and now we can look at the actual like how the system looks like. I'll log onto it and show you around. But before we do that, maybe a quick break if somebody has some questions about what I presented so far before we go into the hands-on part. Okay, doesn't seem there are any questions. Nobody, it's no typing indication from anyone, and nobody has spoken up. So then let's continue. Now I want to switch to a shell tab. Yeah, so here you can see, for example, I just had this open. This is a HTOP running on the DIVF, and you can see all those 11 to 13% SAP worker threads of yate. That is for each of our E1 circuits. One of those threads is eating that much CPU for doing exactly nothing. So that's really, need to fix this. I'm not very happy with that. So yeah, we are now on the DIVF machine. Let's first look at the Osmo E1D that's running here. The Osmo E1D has this telnet-based command line interface that you can log into to look at the state and to introspect. So we can, for example, say show line, and then we see the different lines and the status of those. What's basically happening. Let me just scroll up a bit. So we see the beginning here. Yeah, so we see also counters related to each line, how many signal loss events, CRC errors, whatnot. Since those are mostly virtual lines, these counters shouldn't really increment like the error counters there, because it's all virtual. What is more interesting here is show OCTOI server. So we are running the OCTOI server, and we have various users attached to this. Let's scroll up again. Here you see, for example, in this block here, Christoph, who is here, Christoph's link, and we see via the statistics about the number of train overruns, underruns, and stuff like that, and also that it's accepted, meaning that it's actually up and running. And we get a state. We also see the current round trip time and so on. All of this, we have a nicer way to visualize this in Grafana, which I'll also show you. Just wanted to give you a very quick look at Osmo E1D here. How this works, and you also have a look at the config file and so on in here. So that's not very exciting, but maybe also have a look at where is it, proc dahdi 1, for example. So here we can have a look at the proc file system of the various dahdi devices. So here we see a physical span, actually, that's a Digium T120 card. We see here that time slot 16 is used with HDC. So I think this is the line that goes to the Livingston Portmaster, if I recall correctly, and so on. And if we look at the later line, so this, for example, is virtual trunk to jolly using SS7, and we see that both time slot 1 and time slot 16 are used with HDC and frame check sequence mode, and all the others are clear, meaning B channels in this setup. So that's what you can see on the dahdi side, all these devices. And yeah, so in the end, we have 41 devices now. 16 of those are physical, and the rest is the virtual dahdi devices. Yeah. Now, if we look at the yate side, yate also has a telnet port that you can connect to, where it prints some colorful representation of what's happening, log output, and so on. And you have a couple of commands, not so many commands, and rather cryptic commands. But yeah, here we just see some background traffic, some debug notices about MTP3 messages on the link to Jan. But let's say if I were to make a call now to Jan, actually, you see lots of messages scrolling through here through the log, and it's still far from being completed. Yeah, now the call is actually. So yeah, basically you can see what's happening in the debug log here of yate. If we go back to the beginning of the call, then we see here, yeah, here we see actually the setup message. So yate has a way to decode those messages in the log. So we see the Q931 setup message that's received from my trunk. So I'm also connected like any other user remotely over Osmo E1D over the OCTOI protocol, since the data center is about 500 kilometers away from my home, where we have this co-location opportunity, the sponsored one. And yeah, so we have the setup package, then we see all the different, first the setup ACK, and then we see the information frame that contains the dial number. So in this case, it was unknown number with this. Why unknown? Well, because I'm just dialing the number on the phone, and the phone doesn't know what kind of number this is. And now basically there is digit based. You can see 0000004 and so on. It tries to route the call, and always with one digit more. And in the end, it will actually at some point it will route it here. Yeah, it routes the call, and you see some other log messages about other things that happened before. So for example, that the caller identity is converted to international format and stuff like that is also logged here in this console. And in the end, we make an ISAP IAM call out to the EWSD of Jan. So that's the physical large exchange in the Czech Republic. And yeah, then we say further messages like SS7 messages here, ISAP messages, ACM, CPR. So what is ACM again? I I forgot the expansion of the name. CPR is called progress, alerting, and so on, and in the end disconnect because I hang up the call and so on. Yeah, so we can watch those things in the log, and since it's not everyone has an account on this machine, we recently address complete message. Yes, yeah, I used to know it, but it temporarily slipped my memory as it does when I'm giving talks. So yeah, so what we recently introduced is a now let me. Yeah, Talon. Actually, I have it in my browser history here. So I introduced an instance of Talon, Talon, whatever you want to call it. So we have this address that you can put in your browser, and it will actually give you not with the colors, but it will give you the same log output remotely, so you can watch what's going on the switch and debug some kind of connectivity problems this way, or debug what's happening on the switch. This way. You can also look at the radius log, which is only really interesting if you dial into the port master. We just quickly demo that. Yeah, I guess that really is all that we get here at the moment. There's not a lot of log verbosity going on, but it basically says that, well, first we need to make it larger. So I was dialing the 1234211. No, this is my number actually. Sorry, this is the calling party, and yeah, so that it accepted that. So not very exciting. So the yate log definitely has more relevant information. Okay, now getting back to the console. What we can look at, for example, also is the SAP card configuration. That's sort of the DADI configuration for the lines. So we have at the bottom here, we have the last couple ones that I added. So basically all the called spans in this context. So DADI calls a group of channels a span. Here we have an E1 circuit with this span name, with the signaling channel on 16 and the voice channels on 2 to 15 and 17 to 31. And then we have another one for time slot 1. So you configure these, let's say, B channels here and associate them with different devices. So here we have the physical ones, the TA20. Those are the physical E1 lines, whereas the TrunkDev ones are the virtual ones that we have in this configuration. The next layer up is the Y-SIG-Gen configuration, where, for example, here we have PM3, that's our portmaster 3. So actually it's connected to a different line than the one I was suggesting. I mentioned that maybe the number 1 is the one that uses the portmaster. No, it's number 5 that connects to the portmaster. So we specify that both signaling and voice use this TA2005. That's the name that I gave it in the ZAP card config. So if we do it like this, TA2005. So yeah, this is on the left hand side. The left-hand side, you can see the name of how this was defined as an input line in the ZAP card configuration, and this is the name that we use here in the right-hand side in the signaling channel configuration. Yeah, then there's lots of debugging options enabled, and whether it should store some PCAP file somewhere for debugging, so you can create protocol captures of those, so you can open it in Wireshark and have a better display of the signaling traffic, and so on. And then finally we have regex route configuration, which defines the routing of those calls. That's rather complex. It's based on regular expression matching in a very cryptic, well, some people find regular expressions already cryptic. I'm used to them for decades, But then in addition, all the, let's say, DADI routing specific language here is with the regular expressions doesn't make it easy to read. That's why I put comments whenever possible. So, and then we have these blocks here. So SS7 incoming international. So this is the treatment of incoming calls on an international interconnect with which we only have one right now, the one from Jan. And we basically say, well, we reject if the caller number type is international, is not international, then we will reject it. Or if the called number type is not international, we will reject it because it's an international interconnect. So we don't expect or don't support any other called number types. Yeah, then this is the overlap dialing stuff that doesn't work. And the main route is this here, where we say if the dial number starts with 49 and the next digit is not 0, and then there are 0 to more digits from 0 to 9 each, then we execute the next block. And this line here, what this does is actually it changes the match string. So these rules work in a way that the called number is first put in the so-called match string, which is what is matched against the regular expression here at the beginning of the line. Unless it starts with a variable name, then the variable is matched and not the match string. So if and we change the match string here with this rule. So the block we put between the parentheses, which is this block here, that is what we make the new match string. So we basically strip the 49 at the beginning and we strip the dot at the end, which is the DADI translation of the final F digit, which means end of signaling in ISAP. So basically we changed the match string from the international format to the national format. And then we go to national outbound, basically another point in the routing configuration. So this is how this is expressed here. And then we also have a hack here so that Jan can generate calls to himself back for testing purposes. And if nothing else matches, then we have no route, basically, meaning that, yeah, it gets rejected or because there is no subscriber or no route to subscriber. Then we have a similar route for incoming calls on national SS7. That's what happens when Jolly dials into the system. So here if the called num type is international, then we go to another rule set, or if it's national, the called number type, we go to yet another dial plan, and that then starts here. So you can see it's this all depending on where the call is coming in. There's some processing, and then in the end it goes to, let's say, for example, this national outbound, where then we filter out all kinds of numbers which are not permitted in the German national plan. And if it starts with 30, which is the Berlin prefix, we go to another rule set called Berlin. And if we look at the Berlin rule set, then we see basically the various prefixes for the various users. So we see here, for example, if you dial whatever, something with 6502 after the 30, then it gets routed to Manaworm because that's his prefix and his PBX. And yeah, and we have some others here for playing back tones and so on. Likewise, we have some rules here for DIVF, which gets called if it's a national outbound call and it starts with 4644. That's the prefix for the EWSDF Jolly. When we go to that rule set DIVF, where we then convert some transfer capability to, but where do we actually do that? I think that comment is outdated in this context. At least we're doing this at some other location, the translation. So yeah. Okay, yeah, so that's the cryptic dial plan. And that's, yeah, it is what it is. That takes care of the routing of the numbers. And yeah, that's about it, what's there in terms of yate configuration. We have the zap card config, the SIGCHAN config, and the regex route that put together the rules of what's happening in terms of processing and interfaces and so on. Yeah, that's really it as far as what I can show here. In case somebody wants to see something specific or has questions, please let me know. So Christoph Lauter is stating that he was part of CKTS before joining OCTOI, and he has other prefixes, and whether there's any interest in making those prefixes available over OCTOI. In general, yes, it's just at the moment we would have to do this manually, so we would have to add manual routes, which is fine. I mean, it's not that the number of prefixes changes every day, I guess. So it's a rather static set, I guess. So we can do it manually. I think Christoph mentioned before that he has something in place where he checks the enum route and whether the enum route points to something that gets routed to our DIVF switch, that then he doesn't use IAX to deliver the call, but uses ISDN to deliver the call. That's something that I don't think is possible with Yate, at least not that I would know how it should work. So that would be an elegant solution, but I think without writing code, it's not something that can be done in Yate. So we would have to have explicit manual routes. And it's the question, do we want to do it? Given that, you know, they might get outdated or might not be updated, or so. Yeah. In the end, I guess it's a bit related to whether any of those users or prefixes would want to do something that is more ISDN or data call related, where we would think that there is an advantage of routing it this way rather than the other. But for normal voice, I don't think there's any difference. So maybe as a further explanation, in Yate, there's basically different priorities for different routing modules, and it first goes in our configuration. I think it's also the default. It first goes to the regex route, which is what we're seeing here. And if that fails, or not fails, but if this doesn't find a route, then it goes to the enum route. And so I don't think you can go back from the enum route to something else. That's why we cannot easily implement the same mechanism that you describe. At least I don't think so. I'm not a Yate professional, but the way how I understand it, it's this linear list of priorities, and you have to make sure you do them in one order, and you cannot go back. Yeah, sure. I mean, we can. You can just let me know, and then I just configure it. It's rather easy to do. So as long as it doesn't mean that every week there's some configuration change, it's not a problem. Yeah. Yeah, I'm just saying that's what I meant with. Those should be rather fixed and not change all the time. So then it's fine. So NT2MQU asks whether DIVF is running on bare metal or it's virtualized. So actually we have a bare metal machine called AVST, and that runs DIVF as a QMU-KVM virtual machine, but with PCIe pass-through of the physical E1 cards. So you can actually there's PCI here, and you will see, well, all the QMU emulated peripheral, but then you see the actual real E1 PCIe devices that get passed through this way. There isn't really any specific need to virtualize this, other than that at the time when we set this up, dahdi-trunkdev was bleeding edge kernel modifications that I did, and there always was a chance that it would crash all the time or do some other nasty things, and then you can always debug a virtual machine easier and than a physical machine. So that was really the purpose. But I don't think we really needed it. So it was surprisingly stable. I think I had 2 or 3 crashes initially before we actually went to this co-location, but after that we didn't really need it. But it could, of course, always come again when we update the kernel or do some other changes that we need this capability of debugging the dahdi kernel code. Yeah. So the AVST is a rather there is no additional E1 clock source. Yes, there is. So what we do actually is, well, you can't see that here, but if you look at the wiki of this co-located hub, so what we have here is actually this setup. Well, you have to start actually here. We have this setup, which shows you a nice outdoor GPS antenna that is mounted next to a wall of some, I think it's mostly a climate air conditioned container kind of construction on the roof of this building. And we have actually a garden hose as additional UV protection for the coaxial cable that goes through here, and this goes into the pipe, and we have this GPS antenna here. We only see half of the sky. As you can see, the wall is higher than this antenna, but it doesn't matter. A single GPS satellite is sufficient to get clock from. And then inside, we have a converter from, well, here it's actually antenna connected. It was not connected here. At the bottom is an Ericsson GPS receiver that converts the 1 PPS signal to RS422, which goes over some overvoltage protection devices here. In these yellow devices are overvoltage protection. To make sure we don't get any overvoltage into the building further on. And this then is received by this unit, which is also in the rack. On the left-hand side, you see another really high-end overvoltage protection circuit that I built with spark gap and TVS diodes and so on. And this goes into the Osmo is the ICE1 USB, which has been specially modified with an RS4221 PPS receiver. So we don't use the internal GPS receiver because we don't have coaxial cable between the roof and the data center. And this ICE1 USB then attaches to one of the Digium cards, one of the TE820. And this is the clock master part of the entire system, so that all the physical and virtual ports are clocked off the GPS receiver signal. And that's actually something I wanted to show and I didn't show yet. We have this stats regional networking. Okay, we have this Grafana instance that ManaWorm has set up a long time ago, where we can look at all these counters that Osmo E1D produces. And also we can look, for example, at the GPS receiver. So this is, you can see the number of satellite vehicles. Well, the last 15 minutes is probably not so interesting, have a larger time scale. But here you can actually get all the stuff from the GPS receiver, the signal noise ratio of the individual satellite vehicles, at which elevation, at which point, how many satellite vehicles we had, whether we had a 3D fix all the time. So this is just the monitoring of the GPS receiver that we have. And in terms of the clocks, you would immediately see if somebody does not also have a GPS clock at their end, because then these FIFO levels wouldn't be flat like a horizontal line here, but they would have an angle or a slope, because the clock is running at a different rate at both ends. And then this would show a slope. But even something like this, you can see it's very flat. Yes, there's some noise basically, but it's very flat. So I think not sure if anyone is connected who doesn't have a GPS receiver on right now. I'm not sure. NT2 MKU. He had some slopes in the graph apparently. Well, probably historically, whatever, last 30 days. Yeah. So if we look at some time like this, you can see here the slope. So the clock is completely different, and that, so we see that the FIFO level is decreasing all the time up to the point where it's 0, when then the connection gets reset and it gets reconnected. If we put this here, you can see on the left-hand side, we see frames substituted, and we also should see reconnects at some point. I'm not seeing it right now. Anyway, but yeah, you can see problems from these slopes. So as soon as the GPS is connected, all of the sample clocks run synchronous everywhere, and or well, not synchronous, but at least they run synchronous enough that we don't have these kind of effects. Yeah, so this is sort of the monitoring that we have. We could also look, well, this could of course be expanded, but that's what we have in place at the moment. Yeah, here again we have also the master clock together with the temperature of the system, so you can actually see if somebody opens the rack or something at the data center, and the tuning stage, and also the where is it? Yeah, this is the coarse and the fine tuning value of the control loop that tunes the oscillator in this ICE1 USB. So all of that stuff can be monitored. So if somebody wants to do some research into loop control theory of oscillators or something like that, I'm sure we have a sufficient database by now. And just to put this in context, this identical clock is always required in TDM networks because there are no packets, it's all bit streams, and there are some buffers somewhere, but the buffers will eventually overflow or underflow if the number of bits generated on each side is not always constant over time. Yeah, so here we clearly see there was a big temperature change in the data center, resulting in a big tuning change of our voltage controlled oscillator, obviously, to still stay stable.
There was another question in the chat about security.
Yeah, there is none. Not sure where the question was. I'm sorry, I saw it. Security. Yeah. No, I mean, it's not that there's any security critical stuff happening here. It's a bit like amateur radio, right? I mean, also amateur radio is not encrypted, and it's over the public radio waves. So, I mean, yes, one could work on that, of course, at a cost, meaning that you would have additional overhead if you were to wrap this, for example, in IPsec or something like that. Then all of the optimization that we try to do in the OCTOI protocol would go down the drain. But yes, it's possible, of course. I mean, I'm happy to if somebody wants to do it over IPsec to configure a strong one or OpenVPN or whatever people want to use. It's just that it will inevitably increase the packet size if you want to sign stuff. I mean, encryption doesn't add overhead, but cryptographic signatures always add some overhead. And if you have small packets and lots of them, which is exactly what we have, then it means lots of overhead. Well, yeah, you can also do WireGuard, but it's the same problem. I mean, fundamentally, if you want to have authentication of a packet, then you need to cryptographically sign it some way, and that will add significant overhead to the packet. I'm not aware not aware of any cryptographic network technology that doesn't add overhead on the packets. If you want authentication, which I think you want, because otherwise encryption alone doesn't solve authenticity. So then you still have possibility of manipulation and so on of data. So NT2MKU said, for me, the conclusion was that you cannot create a subscriber setup without any physical E1 hardware. My first idea was to use dahdi-trunkdev on my side to directly feed to a soft switch, but that caused these clocking issues. Yeah, then Manaworm suggested you can use NTP, GPS disciplined NTP. I don't think it's needed. We've discussed this many times. Also, there's many ways how you can have a proper clock. The GPS-based one is just the easy one, as long as you have the ability to put a GPS antenna, of course. But from an, let's say, a development point of view, it's easy. What is always possible is to recover the clock from the packets you receive from the DIVF. You will always get a well-defined number of packets. And if you average the interval of those packets over time, you will have a rather good reference to adjust your own clock. And that can be done completely in software if you want. In the end, what DADI is using internally in the kernel driver is an operating system level timer. And if you do not use that timer, but some other timer that you tune the expiration of the timer based on what you recover from the inter-packet intervals of the OCTOI packets, then you can have a pure software implementation of DADI that runs at a proper clock and where you wouldn't run these slopes that you have experienced. It's all possible. It's just effort. Somebody needs to implement it, but it's not rocket science. Yeah, Manawam says she built a setup using Q-level packet interval averaging, and it works very well. And used an ESP32 to tune a VCXO. Well, that's again with hardware. I said myself in a purely virtual setup, you would then want to tune the I think it was in 1000 hertz, or I don't know the exact interval, but there is one timer in DADI that executes periodically, and you would have to basically adjust this timer to reflect a time base recovered from the interpacket gaps. And in the end, we are not worried about short-term stability. So it doesn't matter whether, let's say, in 1 second you transmit too many or packets or too few of them. It's just that within the size of the buffer, the jitter buffer, you need to basically recover. So it doesn't need to be super precise, and it doesn't need to tune super fast, but with averaging and so on, this should be not a problem. Yeah, with NTPD, Manawam says NTPD in the kernel already has a measurement of the system clock against the real world time. I wonder if you could fetch that ppm offset and just correct for that. Yes, I'm not quite sure how the type of timer that is used in the end by DADI is influenced by that. One would have to look at it. In the end, it might be possible that you can actually just run NTP daemon and you generate a fake 1 PPS source for NTP daemon, and the fake 1 PPS source gets timed by packets received on the OCTOI link. So that basically your 1 PPS basically is created from the interpacket timings of OCTOI frames. It should, I mean, I don't see a reason why that shouldn't work, but yeah, for sure there are many different ways to achieve the goal. Somebody has to sit down and implement them. Yeah, NT2MPU says he tried with the GPSDO master clock with PTP, so that's IEEE precision timing protocol, feeding back to the hypervisor and using PPS KVM with VVX. Yeah, I mean, it sounds like a complete overkill with PTP being used for precision that goes far beyond anything that we need here. But if it works, I mean, whatever you can. There's many ways to solve the problem, as I mentioned. For sure, it's solvable, and whatever method somebody implements first will probably be used. Maximum capacity, well, I don't know, to be honest. We'll see. I don't think we'll reach any problems anytime soon. The biggest problem I see at the moment is the study waste of CPU cycles, because what looks, I looked briefly at the code, it really looks like lazy programming to me. So we can test an easy fix for that, and then we shouldn't waste a lot of resources in the idle state. Of course, then the other question is how many concurrent calls do we have and how many concurrent calls can we handle? I have no idea. It has never been a problem so far. We'll look at it once it becomes a problem. The server AVST, the physical machine, is a rather beefy one. It is a, yeah, you can see an EPIC 7313 16-core processor with 31 threads. So, and if we look at that right now, yeah, you have all these QEMU. I think it's similar, like it's an 8-core virtual machine right now, DIVF, but we could of course use more of the physical cores for the virtual machine, or even run everything on the physical machine if that improves the situation. But at the moment, there's still a lot of CPU capacity available. Also RAM, you can see only 7 of 62 gigabytes of RAM used that are free. So no problem whatsoever at this point. And the other VMs or containers on this machine are really just the Grafana that we're running, and some services for dial-up. There's an OpenVPN as well, and this is actually another Osmocom service that I put on this machine, just because there's a lot of space available, and a Synchronet BBS installation. Yeah, but that's not a lot. So I think we'll be fine for quite some time on this machine, and if we need to scale, we look at it once it's required. But I think a lot of it can be done in terms of software optimization, if at all we reach problems. On the IS1 USB, on the Osmo E1D side, the Osmo E1D needs 18% of one CPU core at the moment, with those 24 subscribers. So you can extrapolate from that when we will reach a limit, but we can just run additional Osmo E1D instances on different ports, running on different CPU cores to scale out. And also in Osmo E1D, we can soon probably reduce the CPU load significantly, since we have been introducing something called IOU-ring into libosmo core. libosmo core is the common library of all the Osmocom projects, and IOU-ring is another type of IO that is not select or poll or ePOL based, how application programs can do a lot of IO, particularly with small IO and many IO operations. So if you were to look in a profile of this, you would see that probably 80% of the time is spent in system call entry and system call exit, because it's doing lots of reads and writes of small packets on lots of sockets. And that's exactly the kind of use case that benefits a lot from IOU-ring. So that will also be reduced. So yeah. So I don't expect any trouble in that area. Might be different when we finally get around, if we ever get around this basic rate interface that has been sort of on the agenda for quite some time, where I guess the potential for many more people would be there to connect, because then they don't need a PVX or any E1 equipment, but just can attach their existing ISDN basic rate equipment, which was much more common and is much more readily available. So you can just plug in a phone or an ISDN terminal adapter or something. And then we would have many more subscribers. So we'll have to look at that once we get to the point. Yeah, it's an overkill. So the comment was that primary rate is an overkill from the end user perspective. It depends. I mean, I guess any serious, I would say any serious telephone connector or PBX user who, as of today, I mean, though they're not so expensive anymore, would be interested in that. At the other far end, you have people whom I will not name here who said, oh, now we have this other project where we use these V5 axis multiplexers where you can in one of those units you can terminate I don't know 400 or something like that lines, analog or ISDN. And there was a comment, oh, I can finally connect all my phones at once at the same time. So it depends on whom you're talking to. Yeah. But yeah, I guess especially people who maybe still some system operators of BBSs, for example, there are some retro-oriented BBSs. I mean, BBSs are retro themselves, but some BBSs that like content-wise are also retro-oriented, like Atari or some other old home computer scene. And they have been interested in this, like in a sense that they could finally have a modem again attached to their BBS and not just telnet dial up. And they would probably be interested in putting such a setup up because yeah, it's just a modem and this basic rate interface device, and they don't need a larger setup. I mean, they're not interested in connecting lots of devices and whatever other things. So that for that kind of use case, for example, it is fine. Yeah, for T1, I have no clue. I know it's much more different than just a different bitrate. That's sort of where I stopped. I did some research once, and I actually used some T1 here, but always with Digium cards that you can just jumper to T1, and I didn't have to bother what that really means underneath it. And my only use case is with some Ericsson GSM base stations that can do T1 as a backhaul protocol. But apart from that, I don't really have any more background knowledge on it. But yeah, it seems a lot more complex, I think, for some reason, but maybe I'm wrong.